All right. Hello, everyone, and welcome. My name is Flo. Konnichiwa, Dacha ni hao, Servus da hinten. Today it's my pleasure to be here. Thanks a lot for the invitation, Greenland. Thanks a lot for organizing this at TAIDA, at National Taiwan University. I am the CEO from Open Hardware, and today I want to give you more overview what is Open Hardware and what we are doing. So for today's agenda, I was thinking, let's first talk about if you really can use open source chips in commercial applications, and if so, where you could use it. And then after this, I want to give an overview, who is the Open Hardware Group, and dive a little bit into the cores, but also make clear what is Open Hardware Group providing as an added value. So let's start. Can you design a commercial chip and ship it in hundreds of million devices? Yes, you can. I took an example application of a mobile phone. Every one of us has a mobile phone. Now, the main CPU today is still some other CPU architecture, which is not too bad. But the thing is, inside this SoC, you have so many different CPU cores, and a lot of the CPU cores already today RISC-V cores. For example, your Wi-Fi or your Bluetooth or your modem to connect, there are many embedded cores which you're not knowing as an end user, and these are already driven by RISC-V. The memory is another example, or also the touch. These are applications you don't know it's a RISC-V, you just know I have memory, I can save all my pictures of my dogs, but you don't know which CPU is organizing it inside. So first of all, RISC-V is already used in commercial applications today. Now, the second example is a SSD controller. Again, a SSD controller inside is quite complicated. There are more than one core inside. You may have something between 2 up to 32 cores. And you have different CPUs like some NAND controller, some SATA controller, or a CPU controller. And these controllers are already today RISC-V. For example, there is a company here in Taiwan, it's called Phison, and Phison is already today shipping with RISC-V controllers for their high-end industrial hard disks. Right, hello, son? Yes. Okay, but what about open source RISC-V? Can open source be used to ship in a commercial product? Many people say no, but that is wrong. You definitely can use RISC-V to ship in a commercial product. Here I took an example. This is a company in Europe, in French, Dolphin Design. They have a design kit where you can design your own ASIC, so they are a design house. And they are offering this design kit where you can really do different applications like audio connectivity and so on. Inside they have different building blocks like a DSP processor, an audio processor, but also power and so on, additional CPUs. All of this can be RISC-V and they are offering it. So I took the DSP here as an example, and you can see in the DSP you have the RISC-V core. This core is actually coming from the Open Hardware Group. Our cores, by the way, originally coming from ETH Zurich. So that is the RISC-V core here inside. But when you're going to Dolphin today, you get your dream chip designed by them, and they can put you open source RISC-V inside, so you fully can inspect it, you fully can see what is inside. Now, a lot of people say, come on, it's just a RISC-V core, it's not rocket science, we can easily do it ourselves. And that is true. It's really simple to design a RISC-V core, and there are so many resources on the internet, so that's the great thing. The problem starts when you want to ship in high volume. Making one core, putting one core in a test chip, like our colleagues from Tsukuba University have done, great, no problem. But when you want to ship 1 million, 10 million, hundreds of million, you need to start with different things. You first need to document the core, so other people in your team know what you have done. Other people 2 years later, 5 years later know how to modify it. Once this is done, you need to start verifying the core, and actually verification to prove there is no bug inside. That's the most difficult thing when you're designing a SoC. So the verification is very often underrated. But then there is a last thing. RISC-V is an open specification. So there keep coming new additions to the specification. Maybe there are things changed in 1 or 2 years. So if you write your own core, you also will need to keep updating your core. And that's again additional work. You update it and you need to start from the beginning, document it, verify it. So not easy. Writing the core is easy, getting it into production, that's the difficult part where you really need to spend a lot of manpower and a lot of time and money. Now the question is, why is the OpenHW Group here? What is our benefit? What is our mission? If you want to make a RISC-V based design today, you have basically 2 choices. You can create your own core, like in the right upper corner, the red one. You have fully control of your core, but because of verification, documentation, and, it is also expensive. You need to have a lot of people. The other chance is you license your IP core from an established vendor. Here in Taiwan, you have Endis Technology in Hsinchu. They are doing a lot of cores, really high-end cores. You have in America, for example, Sci-Fi, and in Europe you would have Codosip, someone like this. You can license your core. You still can customize it a little bit. Your cost is relatively low because you don't need to invest in all this effort around verification, but also your customization is relatively limited. Now, that is where the OpenHW Group is coming in, and we are providing a third option. Instead of making your complete own core or licensing a core, you can take one of our industrial grade flexible RISC-V CPUs, download it from our GitHub repository, and then still modify it as you need. That means you can add custom instructions, you can change the pipeline if you want. You have a lot of flexibility. If you don't want to change anything, you just take the core, you take as it is, you can put it in a SoC. You still need to do some verification, but a lot of OpenHW members have already done pre-verification, so this task is more easier, so in total, lower costs for you. So basically, OpenHW is providing a third option to the buy versus make, something using some open source. Now, maybe let me give you an overview what the OpenHW Group is providing. We are providing first the RISC-V core. The cores itself are written in Verilog, but more important, they are licensed under the Apache 2.0, a very permissive license. That means you can take the core, you can put it in a commercial product, you can modify the core, you can enhance the core, and you don't need to tell us. But the whole idea about OpenHW Group is that if you have some cool enhancements or bug fixes, you contribute it back, we all get better together, but you still can do your custom designs. In the core, we have 3 different families, CVE2, CVE4, CVA6. Like I said, most of them or all of them actually coming from ETH Zurich in the beginning. Then the core itself is nothing without verification. Verification, like I said, super important. Here we are providing an UVM system Verilog 2.0 based framework for verification. It runs with a lot of commercial tools, also with open source tools. However, if you want to put it in a commercial design, most companies are still using one of the 3 big companies for providing EDA tools, so the cores are optimized to work with them, but of course also have recipes for open source like we heard previously, OpenLane, Verilator, and so on. The core and the verification is important, but it's nothing without software. So we are also providing the software, some of our members working on the compilers, GCC, LLVM. We just recently finished the upstreaming for both of this. for some DSP extension, which also came from ETH Zurich before, called the Pulp DSP extension. Then we are also having different real-time operating systems like ThreadX, but also FreeRTOS, Zephyr, just to name a few. And on top of this, there is also Linux support. Now, documentation we mentioned before is really important. That is another point we are working on. And then last but not least, we also have some very basic hardware. On the hardware, we have FPGA images, recipes for FPGAs, and we also did some test chip, which is still in the making as we are speaking. So that is what the Open Hardware Group is providing. Now, who is the Open Hardware Group? Sorry. Before we come to the Open Hardware Group, let me give you an overview about the roadmap quickly. That are the roadmap as we are having it right now. To make it a little more easy comparable, I put the ARM equivalent in the lower corner, and you can see from a very small embedded microcontroller, the CVE2, over an MCU type of controller, CVE4, up to the CVA6, which is an application ready core. We have a lot of different cores. We are also planning some more high-end cores. One core here I want to mention is the CVW, or also CV Volley. I will introduce this later. That is actually a very cool core because there is a teaching book available teaching how to make a RISC-V design from scratch for an application RISC-V core who can run Linux, and that is using the CVW. Okay, after the roadmap, now let's talk about who is the Open Hardware Group. We are a global non-profit organization, and our goal is to host and curate high-quality, industrial-grade RISC-V cores. We are a member-driven organization. Our members come from industrial, for example, like Silicon Labs or Thales, big players, but then also from academia, like ETH Zurich, but also from research, like, for example, CMC or Fraunhofer, or someone like ITRI, for example. ITRI is not yet a member, but maybe one time. What we are doing, we develop, verify, and document the cores in line with industry best practice. That means we really want to make this course available for industrial use for commercial products. The most important point is that we are very member driven. So we are not a normal company where the boss from our company makes a decision. Our decisions are driven by members. I will show you later how this decision process is working. Members in the Open Hardware Group are plenty. You see, for example, ETH Zurich on the upper right, but also companies like Silicon Labs, Espressive, maybe you have heard about them. The Alibaba Group is a member. So we have a diverse set of different members from different countries worldwide. Like before in the talk, open source don't know borders. There are also a lot of academic members. I really like it because a lot of these academic members have great contributions. Harvey Mudd College, for example, but also the University de Minho, who are working on some real-time compilers. So a lot of these people are very active and contributing a lot back or using it for further research. We also have partners in our ecosystem like Synopsys or Cadence who are providing us with licenses, but also other members. Now, if you have this kind of open source, how do you organize collaboration? How do you make sure that people can come and work together? First, when you're having open source, you're enabling a lot of more possible innovation. You allow people to openly explore, to make their own test chip, to check what is happening if I'm adjusting the branch predictor or something else. But having academic and industrial partner coming together also allows innovation where, for example, some idea from research can transfer more easily into a real project. Now, on the Open Hardware Group, we're a platform. That means everyone can come together. There are no NDAs, so don't tell us everything of your secret, but collaborate with other people. Give an abstract idea what you want to do, start making your prototype, and if things work good, then you go with this partner you started, you make your own NDA, you start your own company, or you have it based on this and bring some new ideas into the industry. The Open Hardware Group is organized by task groups. So the main task group is the technical working group. That is really the main where we are making most of the decisions. The technical working group is normally meeting once a month, and then the subtask groups like the core task group where we talk about architecture for the RISC-V cores, how to enhance existing cores, how to bring new cores. The verification task group where we actively develop the verification framework, bring in new methodology, but also see what is necessary to get it moving. A software task group where we are looking for the compilers, but also different operating systems. There are a lot of these working groups. They all report back to the technical working group, which meets once a month. So in these working groups, members attending and members then voting on what is the next project we should do, what is the path we should go, should we implement this new branch predictor, or should we make the new cache system, or maybe both. So that is roughly how the Open Hardware Group is organized. The different task groups are chaired by different members. So here, for example, the Cores task group, Ariane Blink from Silicon Labs is currently the chair. Thales is inside, but also many more members. For academic, it's quite nice to have this interaction between industry and academic. I mean, also for Silicon Labs and Thales, obviously, it's very nice to get all this feedback. It just makes things more smooth. The verification task group, I'm jumping a little bit because we don't have enough time for all the details.
Okay, actually, we can stretch the time.
Okay.
If you want to go through the details, it's okay.
So I can take some more time. Lucky you, I have no plans tonight, so let me talk for another 3 hours. I just want to give this one example of the verification task group, and that is just excerpt. So it's not everything, it's just one example. What we are seeing inside is a lot of different things we are using. For example, the core in the middle, of course, but then there is the Google Random and Structure Generator. And for verification, you see Imperas. Imperas is a tool to simulate your core, so you run it on your core and on the Imperas instruction set simulator, and then you compare if you got the same result. Now this Imperas is really great and it's for industrial use, but it also costs license. For people who don't have the money for the license or just want to explore, you also could replace Imperas with Spike, what we are also helping to develop. What I wanted to demonstrate on this is just that you have a lot of different flavors. In industrial, you still need to use third-party commercial tools for quality, for efficiency, for speed, and that's fine. But in the Open Hardware Group, we also make sure that open source tools are compatible and workable with our cores. The software task group, here we have Ambacosm and the Alibaba group who are chairing this, and inside the software group we are working on different compilers. Like I said, we recently have upstreamed to LLVM the core awareness, so it knows the Open Hardware cores, but it also has the Xpulp integration, which is this DSP extension, and it also can support native hardware loops, which is basically a custom instruction. Some big European companies have already explored this and found that hardware loops can bring a big benefit in saving overhead from avoiding task switching and other things. QEMU, real-time operating system, and Linux support is ongoing. Linux is of course more than Red Hat. I put Red Hat here because Red Hat is also a member of Open Hardware Group. So they are also promoting the OpenHW Group and using our cores for internal software verification, where they can use an open source core, an industrial grade open source, and verify their apps, make continuous integration, CI, to see that what they are building is running on an actual system. Now, there is also an IDE needed. One of our partner called Ashling from the UK, they ported this Eclipse IDE and made it ready to run with our MCUs. FPGA emulation is underway, so the Nexus board, I think a lot of universities have this. That's one of the cool things in open hardware, is that even we are focusing on the RISC-V IP, we bring all these partners together, and that is, for example, something a university could use to say we have an FPGA board, we take the RISC-V core from open hardware, we take the scripts to compile it to the FPGA, and then from Ashling we can use the IDE, for example, based on Eclipse, and get everything together for a teaching course or just for an evaluation course. Now, open hardware, we are working on a tape out. We are making this kind of IoT microcontroller unit. As you can see on the right side, there is our chip. That is the CVE4 or the CV32E40P chip. Then one of our partners has given us an embedded FPGA. There is also a DMA inside and some of the UARTs. The whole design here actually we have seen already earlier. That is from ETH Zurich, the Arnold design, which we have been reusing here. For us, that is something where we want to prove that our IP is working, which is not really necessary, because first it's digital IP, it's relatively easy, but secondly, this chip you're seeing here has over 500 million tape outs from the cores, not from open hardware, but from our members. People who are really putting this in high volume, becoming a member of us, so we necessarily don't need to prove it, but we just thought we are making this chip because it's also good for some of our software guys, like keep developing the compilers. That is helping if you have a real chip and not need to run everything on FPGA, mainly for the timing and things like this. So the dev kit is like here. Like I said, we got, when we taped it out, that was a joint effort between more than 6 partners. So as it happened, if you are organizing a big team, we got some small glitch inside. So we are now making a respin of the chip, which should be available somewhere early next year. Let me give you an overview about the course. I don't want to go too much into detail, just some very high level about the 3 families. Actually 5 with the CV4 with the CV Volley. But before I go into the course, I want to bring up a term which is the TRL. TRL stands for Technical Readiness Level. In open hardware, but also in a lot of other companies, TRL is used to analyze the quality of the chip or the status of a chip. So for example, when we got the chips or the RISC-V designs in the beginning from ETH Zurich, we classified them as TRL3. The design was done. ETH or Pulp platform team made a tape out. The chip was working, maybe some minor issues inside. So we had a proof of concept. But this proof of concept is nothing which you want to bring into production if you're making hundreds of millions of chips. So you need to start to verify it. That's when it moves to TRL4, when you're verifying it somewhere in the middle. And when you're done with with verification, you have no coverage holes inside. Then we are declaring it TRL5, which means the system has no bugs, no coverage holes, nothing. It's ready to put into production. And then actually our members taking it to TRL6, to TRL7, and even to higher qualifications. So this TRL system is very good to have a first impression on the quality of the IP. If you're a hobbyist, TRL3 is really great. It's good. You get a running chip. But if you want to make hundreds of millions, you need to have very good verification. You need to go a little bit higher. Just wanted to throw in this terminology. It's quite useful and widely used in the industry. Now coming to the cores, the first core we have is the CVE2. That is a two-stage in order pipeline. It is really optimized for deeply embedded applications. That is actually the coming also from the ETH Zurich. It is also used in the low-risk OpenTitan project. It is called IBEX there. A really great core. If you don't know low risk, you also should check them out. They do really great stuff for root of trust and so on, ready to take designs. Taiwanese company Nuvotech has made a chip with them. Google is putting them now in Chromebooks. So that is really where open source is used as a root of trust to verify things. And if you want to put it in your own design, welcome to check it out on the OpenHW Group. The project goal is TRL5. We are currently in TRL4, so it's not fully verified yet. We're expecting to have it fully verified within the next 6 to 8 months. On the GitHub there, you also have a project repo. That means you can check out the project repo. There is a project management inside and everything, which gives you the current status. The next core is the CV4. That is a 4-stage in order single issue again. What is the cool thing here is that we have different versions. So the version I'm showing here is the version optimized for security, something like, again, a root of trust or so. It has a lot of security extensions inside, and it also has a special extension for custom security. Now, this chip has a few different versions in OpenHW. We have one for the security. We have one for IoT applications where the DSP chip is inside. And there is also one version which is made for accelerator-based workloads where you have interface to connect an accelerator quite easily. The next one I want to introduce is the CVA6, a 6-stage in order single issue, again from the ETH Zurich. They called it Ariane Core. We have renamed it to CVA6, Core 5 application 6-stage CPU. Maybe the name is not the easiest one, but kind of tells you about the core. This core, we are working now on TRL5. There are some big companies involved, also in Europe. By the way, the European Union has also selected this course as a baseline. So a lot of European companies get money to develop based on this course or to help to verify it, to make it available for other startups in Europe. But however, because it's open source, it will not only benefit Europe, it also can benefit here. It can benefit in America, wherever you want. So that is a great thing in my personal opinion. Now, the last core I want to quickly give an overview today is the CV Volley core, or CVW. That is currently also in TRL4. We are preparing it for TRL5. And this preparation is, by the way, that means we are having a weekly call. There is a university driving this right now. So we have a weekly call with our in-house verification expert where we align on the strategy, what are the next steps to do to verify how to close the last open holes, coverage holes inside. This core also can run Linux. Now the cool thing is that there is a book available about it. The book, you can see a picture here, Digital Design in Computer Architecture, RISC-V edition. There are other editions, but you only are interested in the RISC-V edition. And this book is really teaching how to create a core from scratch. And in the end, when you finish the book, you should have replicated the CV Volley core. Now, some secret I can share with you. There will be a new book, RISC-V System on Chip Design. The same authors, but this time they are making a SoC and are teaching how to make a complete SoC with peripheral. So if you're looking for some teaching, which we had in the beginning, the question how to do this, that could be a good starting point. But also if you want to learn more about RISC-V, I highly recommend to buy the book. I bought myself. It's really great for reading and for getting more information. Okay, that kind of brings me to the end of my presentation. I really hope you are choosing RISC-V from Open Hardware for your next design, no matter if it's research, if it's a product you want to create. Our products are open for both, and we are having a platform where we are enabling the coexistence or the sharing between industrial and academic institutions. The cores itself are fully open cores. That means the RTL, but also the verification, plus the documentation. So let's work together. Let's create this RISC-V course together. Let's create some new innovative things based on RISC-V. That brings me to the end of my presentation. Thank you very much for your attention. If you have any questions, feel free to let me know. And thanks.
Any questions?
Yes, one question here.
Okay.
Is there any clear debut date about the new RISC-V SoC book?
No, it's only in end of Q1 next year.
Okay, thank you.
Thank you.
So I see that your core is provided by the. Well, I think it is a page that I think is a CVE4. That page that the 32 bits core and the 64. Sorry, next page. Yes, I see that there's 32 bits and 64 bits come from a different provider. One is Zurich, and the other is Telus.
That is correct. So the Ariane core originally came from ETH Zurich. It was a 64-bit system which you could configure, and the guys at Pulp Platform team made some really great designs with it. Then we took it to, or we got it donated to the OpenHW Group, and with our people we started to verify the core, to add some missing points. Now some of our members, like Thales you mentioned, they came and they said, we love the core, it is great, but it is still too big. We make a kind of more embedded design. We don't need 64-bit. We need 32-bit. We have a commercial application which we run in high volume. And so having 64-bit or 32-bit makes a difference in gate count. And if you create millions of chips, this difference is apparently big enough to say we want to scale it down to 32-bit. They also make some other options. They don't need an MMU, for example, so they also remove or make a configuration, so you can say compile without MMU. And that's why this core looks like it's coming from Thales. It originally came from ETH Zurich, but we are working all together to create more versions or more different use cases. That is, by the way, also something very interesting. I heard one gentleman just told me that he said the 64-bit is great. It runs perfectly for accelerators or AI workloads, which is where RISC-V is used massively. But if you want to bring it to more embedded application, even with Linux, you still need to have a 30-bit version of it. So there is now some porting ongoing, and there is a lot of fight on some software mailing lists because they say we don't need 32-bit, we only need 64. Who is using 32 anyway? But these guys are arguing with technical background and say, look, it's a cost question. If we can make it 32-bit, we can save a lot of cost, and for the next years for an embedded device, 64-bit is overkill, maybe, for some applications. So having this in software support off the shelf, so upstream software support, is very important for them. But again, that's the great thing about the OpenHW Group. We have a starting point, and then we are developing it, driven in an industrial or commercial direction.
No, I have questions.
One or many?
Well, just Because I recently noticed that the hypervisor extension is officially merged into the CVA6 code base. So, and I saw the 10x engineer, one of the member of OpenHW Group have provided the RISC-V IO MNU. So, just wondering that will there be more ASIC tapeouts that will include hypervisors and the IOMU part in the future, or well, just curious about it. Yeah.
Yeah. So the hypervisor part was added recently. That is also partly driven by C. Ailetti, someone like E3, but in France. There is also other groups inside, like again, Thales has a little bit pushing there. So we will see tapeouts of this. The question is if we will see it in commercial products. So, or to put it in another way, we will see it in commercial products, but maybe you cannot buy the CPU off the shelf. So maybe it will be something more embedded, but definitely there will be more tape outs with these features.
That's very good to hear, because RISC-V hypervisor and its IOMU is basically like a myth. We all know that there are people taping out. We all know that there are products using the RISC-V hypervisors, but we can never know exactly who made it and who taped out it. So it's good to know that OpenHW Group is working on this.
There is maybe one to add quickly something. The hypervisor also, it will maybe it will be available in a chip, I don't know. Maybe a member make an off-the-shelf chip, that would be super cool. So if you want to make a company and want to make an off-the-shelf chip, you're welcome. We are happy to support you. This chip will also be working on an FPGA platform. So we are making an image. You can configure 2, 4, 8 or more chips that will run on the Amazon FPGA cloud. So on the Amazon FPGA to make it more fast, but you also can run it on your home FPGA if you have a big enough FPGA. That means you will be able to test the hypervisor on FPGA at least. And you will have some real products later, but for software development you can test it.
Speaking of the SMP, I believe the SMP part is coming from OpenPython, right? The Python, the Purdue University provides the logic of SMP. I'm not pretty sure, but just curious.
There are many different ways you can choose. We are working currently with Professor Jonathan Balkind. He is now at the UC Santa Barbara University. He came before from Berkeley, where he developed OpenPython. He kind of is the maintainer of OpenPython, and we are using OpenPython as the interconnect for the SMT. OpenPython is a directory-based network on chip, basically, with also caching and so on. It can scale from 1, 2, up to 1,000 cores. So, and that's what we are using for the FPGA image.
I see. Is there any questions? Oh, from.
And do you have any project for educational purpose? For example, a core for educational purpose to help college students to learn how to design a hardware? Yeah.
Professor Chen, that's a very good question. We don't have a course material right now. We do have the open source hardware, and the CV Volley with the textbook could be a good starting point. But what Philippe said before, the ETH Zurich is now developing this teaching on the Croc platform, right? So I think that will be a very good resource. At the OpenHW Group, we are expecting that people who are using it have some basic knowledge about how to make an SoC design. So it's maybe not the best for teaching students in the beginning. However, if students have some experience, I think it could be a good material. The manual is good just for the beginning teaching, something like a 101 on teaching or making a RISC-V CPU. We don't have at the moment. But the ETH Zurich, I believe, will be good material which can be used.
I want to ask, if you want to ship the million or more than 1 million of chip, then I think there will be a requirement for the test after and test and verification after manufacturing. But I think this was one of the part that open source tool cannot cover. Like a scan chain or something. We don't see any discussion about this in the tool supported.
I'm not an expert for this. What I know is that we don't have any DFT design for test in the OpenHW group. There are a lot of commercial offers, like Siemens, for example. Siemens is also a member of OpenHW group. They have the scan chains and all the insertion tools and everything. For open source, I am not aware that it's available so far. But it's a good point if you really want to produce industrial grade CPUs with fully open source tools, open lane, PDKs, very later, and all these things is an important step, but it's not everything. We will need to have much more to also make it testable by third-party test houses in Malaysia, in Italy, in wherever they are based. And that's at the moment a missing point, yeah.
Yes. Okay, thank you.
Hello. I have a question about and the projects of open hardware. I find it like, for example, CVA6 is supporting more and more extensions, and does it mean like the verification effort of the open hardware group is like bigger and bigger? And because you say you are member driven, so it's like member will request for more and more extension, and how do you manage the bigger effort of verification when I mean the effort is bigger and bigger, and how to deal with it?
Yeah, that is a very good question indeed. As we are adding more extensions to our RISC-V cores, the verification effort become bigger and bigger, and also the time of verification become more. You need more licenses of the verification tools, you need more CPU power to run it. That all is a lot of additional cost. We are handling this in two ways. So at the OpenHW group, the CVA6, for example, we stopped completely verifying it in OpenHW. We are still verifying it, but not daily, because it's just too much work. We cannot do this. We are depending on the different members who are adding this. For example, we heard that Thales is adding the 32-bit and also hypervisor. So Thales is maintaining and updating this in the OpenHW group, but Thales is running the main verification. So Thales, for example, every week verify all the extensions they have added and then share in the OpenHW group, yes, everything is passed or we have some failure. Now, other people who are adding extension will also verify their part. In OpenHW group, we make sure we get all the reporting together and make sure it's covered. Once we will generate a new version of the core, like a stable version, making an official release like 1.0 release or 1.7 or 2.0, then OpenHW group will run the verification on our side. But we will not run the daily regression because it's getting more and more complicated, and we are also not having the CPU power. So OpenHW, like I said in the beginning, we are a non-profit organization. We get our money from members who are paying us to be a member and also helping us to verify it. But the money they are paying is not enough to run daily regressions someone like Endis could do, for example. So our members will run most of the regression, and we are only running it when we have a big release. But very good question.
Thank you very much.
Because the board from COSCUP' is pressuring me to close this. So if you have more questions, please feel free to ask him, but I need to wrap up the hardware.
All right, so we need to finish because we are kind of late. But thank you very much, everyone, for joining. It was a pleasure to be here. And also COSCUP' was really nice organization. I'm looking forward for next year. Thank you, everyone. Have a good day.